Swayam Prabha. Digital India. Educated India.
Welcome to the week 7 lecture of the course Foundations of Cyber Physical Systems. So, if you remember in the previous lectures, we have been talking about the basics of hybrid automata and how hybrid automata can be used for modeling cyber physical systems. And the next important thing we want to talk about is, we saw how hybrid automata can be used for modeling CPS. There are so many tools using which you can actually simulate CPS models of hybrid automata. But what is also important is you will like to reason about such models and figure out whether at the model level these systems can have some specific desirable properties like safety property, liveness property and others, which we will see what those things mean. So, this part we will be covering in this week under the header reachability analysis of hybrid automata. So, just if you remember the different examples of CPS that we talked about earlier, we can have a CPS which is implemented as a controller scheduled over a compute platform, and it is computing control signals for multiple plants, and there are communication between the plants and the controller happening through this kind of networks. Also, we can have complex physical systems in the form of a smart grid, where you have electrical appliances inside a home, and not only these appliances which are the consumers of the electricity, but also there are some small producer systems like solar PVs and others which are present in a modern home, and there are other consumers like modern loads like the electric vehicle loads, and they are kind of provided the power through a smart grid. And there are several problems in this domain like electricity scheduling, safe operation of the generator, figuring out whether the generator of the grid are working inside their safe operational limits. All these problems can also be modeled as hybrid automatons. Now, like we said earlier, that it is not only the case that I will like to model them using hybrid automata and use a hybrid automata simulation tool for figuring out how, given an initial point in the system, initial state in the system, how does the system's trajectory evolve over time. I will also like to see that, assuming that the system can start not only from a state but a collection of such states, a collection which can possibly have infinite number of initial values, where does the system trajectory go? What are the regions in the state space of the system that the system trajectory will diverge, and whether those regions are safe operational are safe operational or not. We will like to know all these things. Now, of course, you can understand that the moment we talk about a region of the system as an initial region, that the system can start from an initial region which is a collection of infinite number of states. I cannot really simulate the system for all those initial states and figure out whether the system is safe. I would rather like to have some formal method through which I can analyze whether the system state is having a safe trajectory, where it can be, the state can start from any of those initial states which are part of the initial region. So, we will define what these things mean. There are also several other applications like automotive systems, where you can model the different vehicle control loops using hybrid automata and figure out whether the design of the control, along with the delays that can happen on the control side or the sensing side, whether with all those uncertainties in the platform, the overall system is safe or not. So, this is the primary reason why we will like to talk about reachability analysis of hybrid automata. We will try to figure out that, since it is not possible to simulate the system for all possible starting states, because the set of starting states can be infinite, we will like to have this kind of automated reasoning based methods through which we can analyze whether the system is safe or not. We are not claiming that that can be done for any complex system, but there are methods through which this can be addressed for some practically for many practical systems where the complexity is kind of abstracted out and an analyzable model of that system is created using a subclass of some hybrid automata. We will see that. So, we will restrict ourselves to this linear case. That means we are talking about hybrid automata where the dynamics of the continuous variables is always linear. So, let us understand what it means. So, we will go back to the definition of hybrid automata, modify it a bit. So, of course, the modifications are not going to happen on all the tuple elements, on some of them. So, we will have our set of locations, okay, and there is one small notational change we are doing. Earlier we were talking about this set X as the value space of the continuous variables, right, but now let us use this variable X to be representative of the set of continuous variables in the system. So, suppose you have 2 or 3 flow variables in your hybrid automata. Those are the variables that comprise X now, and the discrete switches are modeled by transition relations, which will make the automata jump between locations that are in L. So, in that way we will have a transition relation like this, and then what we have is the invariant set. Now, the invariant set is, if you remember earlier, we told that invariant set again for a location, it means that a region of the state space for the continuous variables in which the system if the system is in that region, then it is allowed to be in that location. So, that means if I am in the location, I must satisfy some mathematical condition which captures that region. Now, in this case we will restrict it to be convex linear predicates on the variables. We will soon describe what it means by a convex linear predicate. Now, the next thing is the flow relation. So, for every variable small x inside capital X, we will have a flow relation like we defined earlier, that a derivative of x is given by some flow function which is f, which is defined based on for each location and for each continuous variable we will have this flow function. Now, since this is the linear case, we will assume that this is a constant. So, what it means is that for any such variable, so if this is time and let us pick up some variable x, let us say initially the value was here, is going to increase with a constant gradient. Okay. So, this gradient is basically a constant value which is given here. Okay. So, that is how we will now abstract it out. I mean it does not increase like this or like this or like this, it does not increase like this. So, that is what we are talking about here. Now, the next thing is, this is similar, we are talking about valuation function. Now, what is valuation? It is a function which tells that at any time instant, each of the continuous variables who are going to assume some real value, like what is the value. So, that means suppose I have continuous variables x1 and x2. So, at valuation of x1 at time t will be something, and valuation of x2 at time t will be something. Let us say this is 3.9, this is 4.2, like that. Okay. So, of course, x is an n array set, then this is like a to the power n, or I mean sorry, yeah, this is for each variable we have a corresponding real value here as given by this valuation function. The next important thing is for any transition. So, let us just try to create a transition here. So, assume these are my locations. So, this is one transition, let us call it T, right. Now, this transition, like earlier, they can have a guard and a reset. Now, this guard, let this be the transition T, and there is a guard GT. It is a convex linear predicate defined on the variables. So, we will need to define what is a convex linear predicate. We will do that. Just wait a minute. For the time being, it is just a constraint defined over the variables in X. Okay. Now, when we say convex linear predicate, it is a specific class of constraints. So, like we discussed earlier, valuations, I mean they give me values for the real variables. Invariant set, guard, they represent a region in the state space of those variables, and the region is always captured by a mathematical relation. In this case, we are focusing on the relation being a convex linear predicate. The other thing is the reset set. So, just like guard, we will also have the reset set. For example, let us say this reset set is containing x1. That means, when this transition is taken, let us say here before the transition was taken, the valuation of x1 was some 4.5, let us say. The moment I take the transition, the valuation of x1 will be 0. That means, it will restart its value, it will restart its increase of value from 0 the moment I get inside L2. Okay. Now, coming back to this issue of convex linear predicate. So, what it is? So, a convex linear predicate is a system of linear inequalities over a set of given variables. So, let's write a structure for them. Suppose you have variables x1, x2 up to xn, and let us say there are some constants a1, a2, an. So, it is a linear combination of these variables and constants. Linear combination, that means it can be something like this. Okay. And they are related with some constant here. I mean, in the general case, you can push it in this side and have a 0. That is also, I mean, some books will describe it that way. Now, what is this? This represents a relation which is any one of this. So, you can see that it is a linear equality or inequality relation defined over the variables and with some constants. So, that is a convex linear predicate. Okay. Had there been only 2 of these variables, it would be a subset of such convex linear predicates. I mean, or more in general, we will, I mean, this, when I write this, it represents what we call as a convex polyhedrous one surface, and there are many subclasses of that which we can define later on. Now, of course, this is one such predicate. Now, we can of course keep on combining such predicates. So, let us call this some P1 . So, when I say overall what is a convex linear predicate, it is a system of such linear inequalities. So, I wrote one of them, right. So, in general, when I define any convex linear predicate, it can be a conjunction of such linear inequalities. Okay. So, let this be some P, and in general, so this is a convex linear predicate. In general, when I define a linear predicate, it would be a finite disjunction of such convex linear predicates. So, overall when I have say some linear predicate, it is basically let this be P along with some P prime and P double prime like that. Okay. So, what we did is we defined those linear predicates in terms of linear inequalities over the variables. Their conjunction gives me a convex combination, that is a convex linear predicate, and a finite disjunction of such convex linear predicates gives me this kind of linear predicates in general. Okay. So, that is how we define it here. So, this is how we will restrict ourselves to this general subclass of hybrid automata. Let us call this the linear hybrid automata. So, as you can see, we call this linear because the flow relation is linear and we have all the constants defined in terms of these linear predicates. Okay. Now, this was just a tuple definition, right. So, it will also have its semantics just like earlier. So, it is like this: any predicate P which I define on the variables on the variables on X, it is true for some specific valuation, right, because the variables are assigned the real values using this valuation function, right. So, what it does is, given a valuation function, I can interpret the predicate P, right. So, let us say the predicate says x minus y less than equal to 2. So, let us just write it here as an example. Given a valuation function, I have v x and v y, and if those values are let us say 3 and let us say 2.5, then this is true, right. So, in that way I have to interpret the predicates over specific valuation functions. Now, similar to this idea, since my invariants and guards are all convex linear predicates, I have to interpret them with respect to a location and the valuation of the continuous variables in that location, and figure out whether the invariant in that location is true for the given valuation, or similarly the guard of some transition t is true for the given current valuation of the variables. Okay. Now, this next statement gives me a symbolic encoding of resetting of valuations. So, if you remember, when we took a transition here from one location to another, we have an associated reset set, right. So, if that is y, this notation v y reset to 0 means I am going from the set v of valuations for the variables to a new set of valuations for the variables, where the variables present in y get initialized to 0 and all the other variables have the same valuation as it was in the original v. Okay. So, that is how it is defined. Now, if the system starts or enters a location L with a valuation v, then after some time tau, the valuation is given using this relation. So, it is v x. So, suppose I am talking about the valuation of some specific variable x. The system has just entered a location L, and after entering the location L, tau amount of real time has passed, right. So, I want to know that at this moment, after this tau amount of real time has passed, what is the valuation of this variable x. So, it should be the original valuation, which is v x, plus the rate of increase of this variable x in the location L, which is a constant as per the definition of linear hybrid automata, multiplied by the time elapsed, right, which is tau. So, I think this is quite clear. So, in general, such a time elapsing operation is denoted like this, that I am in the state L v, that means I am in location L and presently my valuation of all the variables is captured by the function v. After elapsing of real time of amount tau, my state is L v prime. where V prime is nothing but all the original valuations in V for each of the variables increased by an amount that is tau. So, that is what is denoted by this. Okay. I mean, you can just write plus here, here it just means that this is happening in the location L, nothing different than that. This has no hidden meaning, etc. Now, for a transition L prime. So, whatever we discussed earlier, we are just now bringing in the notations again. We have a discrete step. So, earlier what we defined was the time elapsing operation, now we are talking about the discrete step. So, suppose here I am taking this transition A. Okay. So, I have this discrete step with this transition of level A between two of these states L, V, and let us say that I jump into L prime, and the moment I jump into L prime, whatever is my valuation is given by V prime. Now, this situation that I was at LV, I made a location switch, that means I took a discrete step or discrete jump using this transition with level A. So, exactly this is how it is being described in formal language. So, from this state I jumped to L prime V prime, it involved a location switch using this discrete state transition A with label A. Now, let us say this transition has some guard G. Okay. Now, this transition will be possible only if at the time of the transition, if my valuation was V, this valuation is satisfying the linear predicate which is the guard here. Okay. So, like we discussed earlier that the guard and invariants are also convex linear predicates, and whenever I have a transition, the guard has to be satisfied, right. So, this transition is only possible if at the moment of the transition the valuation V is actually making this guard condition, which is this linear predicate, to be true. And also, how do I calculate V prime? You will calculate V prime exactly using this operation. So, as you can see that this is why we have defined all these things, that when is guard true, when is invariant true, how to write the reset, because they are in turn used to define this discrete step, right. Because now V prime is nothing but V with the modification that whatever is the reset set of this transition with level A being set to 0, right. So, whatever variables are in reset, they will be starting from 0 when in V prime, and all the other variables that are there will just have the original values as it was in V. So, this treatment of LHS semantics and whatever most of the things that we follow have been taken from this material, reachability verification of hybrid automata, by T. Henzinger, and there are many co-authors in this. So, in general, this is how a run of the LHA would look like. So, let us say your initial location is L0 V0, right. I mean, initial state is in L0 V0, where the location is L0 and the valuation is V0, and you make a discrete switch to L1 V1, you may elapse some time here, then again you make a discrete switch like that. So, typically here we just show the discrete switches, and in here we show what is the transition level along with the time of the transition. So, typically that is how an LHA run is being described. Okay. Now, one thing we must remember, that this initial state L0 V0 should have the valuation such that it satisfies the initial locations invariant or the initial state init, that is of L0, that what is the initial condition of L0, that init set. If you remember, it was discussed earlier in the definition of hybrid automata, that when I am starting from a state, what is my possible set of initial valuations, and then in the initial state I will have a possible invariant, right. So, ideally both these things have to be satisfied, the initial condition as well as the invariant of L0. We will see that. I think it is also discussed in some of the previous lectures. Okay. Now, when do I say that a state is really reachable? I would say that a state is reachable if it is the last state of some valid run. That means, it is possible to start from some initial state comprising an initial state, like we have already defined. It means that I am in one of the initial locations and my valuation satisfies the initial condition of the automata as well as the invariant of the initial location. So, I start from a valid initial state and I may make suitable time elapsing transitions like this in the different locations, and I may make suitable discrete steps to jump to different locations, and in this way I finally reach a state. Then I would say that this state is reachable. So, for every state to be reachable, such a run has to exist from some initial state up to that state. As you can recall that any state just means it is a collection of location and valuation. Okay. So, in general we have this problem which is what we call as the reachability problem of linear hybrid automaton. So, it says that suppose you are given this kind of an automaton A and a set R of linear regions. Okay. So, it is a collection of linear regions. So, that means they would be represented by a linear predicate like we discussed earlier, right. And a linear predicate like we discussed is it can be a disjunction of the convex linear predicates, and the convex linear predicates are nothing but conjunction of elementary convex linear predicates, or basically the linear inequalities. Okay. So, the question is, suppose I am given this A and suppose I am given this set R of such regions expressed as the set of expressed using linear predicates. Is it possible for the system to reach that set? That means, can the system start from one of the valid initial states of A and have a run like this to reach some point that may point in the state space, or alternatively a state which is inside this set R. So, that is the reachability problem, and we want to understand how to solve this reachability problem. So, fine, we will stop the lecture here, and maybe in the next lecture we will start from this reachability problem and a technique for going about solving. Thank you.